So I use time temperature transformation graphs or time temperature transformation curves to really understand and teach the effect of cooling from a molten weld pool and within the heat affected zone down to room temperature, what its effect will be on your final grain structure of your steel. And then that's going to give us a really good idea of what additional processes or controls do we need when we're welding. And that is, we tie into what we call weldability. So something that has a really good weldability generally has a graph that looks one way, and one that has a poorer weldability has a graph that looks another. And this is where we see what that looks like. So jumping straight into it, what we've got here is the by the book time temperature transformation graph. And you can see it's quite busy. There's a lot of things happening and a lot of things going on. But when I'm teaching weld inspection and the weldability sides of that, the metallurgy sides of our weld inspection, it's a little bit too much to take in one go. So what we do is I draw on the board all the time a simplified version that really captures the essence of what's happening. So what we've got is, you can see one side is temperature, one side is time. We've got our melting point, which of course is slightly different, depends on the alloys and stuff like that. Let's say 1500 degrees. Above that, we've got liquid, so our material is molten, so there's no grain structure. And as it cools down on the temperature, you can see we've got this austenite region, which is, there's enough energy in the material to have a grain structure, which is austenite. But then as it cools down and we get to what we call the critical transformation temperature, carbon steel's normally around 723 degrees, we're going to see a change from austenite to something else, to the final grain structure in our material. Generally this is in the heat affected zone, right? So as it cools, it goes through all these points, and then it's going to end up as either martensite, bainite, or pearlite, ferrite, seminite, bainite E-mixes. Okay, so let's have a look how that happens. So like I say, so 723 degrees will just stick in as our critical transformation temperature there. So we cool down after welding, so this is immediately after solidification. And yeah, okay. Now a slow cooling rate is generally where we want to be. On the official TTT diagram, you'll see time is not evenly spaced along the axis. It's a logarithmic scale, so it goes up in 10 times values. So 1 second, 10 seconds, 100 seconds, 1,000 seconds, etc. So it's, it's difficult to really show you what that temperature would be, and it's different for different steels as well. But generally we say a relatively slow cooling rate. This is left to cool in air is maybe a good example of that. And it gets us where we kind of want to be. If it's slightly quicker, then it's going to be bainite. So these areas tend to be the sort of middle outwards of the heat affected zone, because this is where we're getting a cool and a quenching effect from colder material to the outside, speeding up the cooling rate, where the weld metal is keeping the front half of the heat affected zone hot. So you've got, the thing to remember here is that in a heat affected zone, it's not consistent all the way along. There's different grain structures being built from the fusion line in contact with the weld metal out to the parent material. And if we sort of quench it, now this could be in water, in oil, blowing cold air at it and stuff like that, we're going to have a fast cooling rate, which is going to give us our martensitic structures. These, in a welded carbon steel structure, is generally something we don't want. It's going to run the risks of brittle failure, hydrogen core cracking and the likes, and we generally don't want it. But in some materials it has its uses, martensitic stainless steels, high wear resistant items and stuff like that. Carbon steel, let's keep away from it. Now, I keep using the term carbon steel like it's all one thing, but we know it's not. We have different grades of carbon steel. You know, we start at the S235, 275, up to 355 are our general sort of fabrication, you know, general purpose steels, if I can give it that term. But we go up in strength as well. Now, one of the ways we can increase strength, let's say from an S355 to a 690, which is a really high strength steel, would be to add more carbon. That's going to affect, that's great. Now, in doing that, we make the material harder and we lose weldability, right? And we kind of capture the increase in strength by adding stuff as a term we call the carbon equivalent value. And as we increase the carbon equivalent value, or the CEV, we have an effect of moving our martensitic, well, all of our bands, but definitely our martensitic, move to the right. So you can see here, by doing this, we have to cool even longer to get into our pearlite, ferrite and selenite structures. If not, we're more likely to hit a martensitic band. Okay, so increasing carbon equivalent by increasing our alloying elements to get higher strength has a direct change to our TTT diagram, and we can use that to understand what we have to do. Now, instantly, what we can see here is an increase in CEV is going to increase the preheat values, because by preheating a structure, we get a longer cooling rate, and therefore we're more likely to be where we want to be, not in the martensitic band. Yeah, and we're going to come to preheats in a future video, and around a standard called EN 1011. 1011 is a great standard if you want to know, generally good control within welding. 1011-1 has general rules, and then 1011-2 is also a good one to pull into. Yeah. So I keep saying, the addition of alloying elements and stuff. Now, what I've shown you is the major one for us, which is a move to the right on the graph, but different alloying contents will move the graph left, right, up and down. And here's some of the large ones here. You can see that moving the graph to the left, to the right, the martensitic becoming longer is going to be our carbon there, definitely, but then our manganese, which is a big adjuster and a big thing we add to steels to increase strength. You see you've got the also common ones like nickel and chrome. But some things which are non-metallic, like silicon, which is used as a deoxidizer, that is all going to make the weldability less. So it's going to be harder to weld. Some things move it down and some things move it up. And you can see that some of them cross with each other. So manganese is actually going to move it to the right and down. Chrome is going to move it to the right and up. And then that will give us different aspects. But in the main, like I say, we're more worried about it from a welding side, moving to the right in general. Okay. Now, we talked about CEV, but what is it actually? Now, most of the time you don't need to memorize this, okay? Especially when you look at, say, your 3.1 and stuff like that. It's not a remember it and write it down or pick an answer or something like that. But you need to understand what it affects, which is what we've seen. Carbon equivalent affects the weldability of the steel, and a higher CEV will increase the hardenability, so decrease the weldability. But there you go, there's the equation. There's a couple of different equations. This is the IIW, so the European version of it, and that will keep us running. Now, as an example, here is a grade of steel. So you've got your chrome and manganese, your silica, phosphorus, sulfur and nitrogen. So this is a very standard carbon manganese steel. And you can see that we put the values we can into the equation. Not everything is there. In our grade here, we don't have chrome, moly, vanadium, nickel or copper, so they would just be zeros in the equation. The main ones here are our copper and our manganese. And then we get a CEV of 0.2%. Yeah, that's relative. That's going to be okay to weld. No real concerns. Maybe when we think about thickness, we might have to account for something, but in general, it should be quite weldable. And if we add additionals in there, then we're going to have to account for it. The silica, phosphorus, sulfur and nitrogen, you can see don't form part of the equation because they're not affecting the weldability from a hardness issue. But they will do other things. You know, phosphorus and sulfur in particular are impurities, non-metallic impurities that we want to drive out as much as we can. So you can see the numbers at which we sort of see are our maximums. Often where we try to get as low as possible. So as a very quick summary, what have we got? Well, time temperature transformation diagrams are great for understanding the effect of cooling, right? And they help us visualize the requirements for preheat and slow cooling items we might want to put in. We can instantly see that if we have a high carbon equivalent, it's going to push everything to the right, and I'm going to need to have a higher preheat, or I'm going to need to slow cool in an oven or fire blankets over the top and get it back to that line crossing the perlite ferrite section of a graph. Well, that's it really. It's a fairly straightforward body, but if you can remember the effect of that and visualize it, then you're going to be able to answer a lot of questions in multi-choices, especially around hydrogen-induced core cracking, in hardenability and weldability within your exams. So with that, thanks so much guys, and good luck with your studies, and we'll see you next time.